this chapter, we will be introducing the concept of integration. In this lesson, we'll be using antidifferentiation to find the area under a curve.
Okay, hi everybody. Now what we're going to do is we're going to take a look at one of the more interesting applications of antiderivatives, and that's finding the area under a curve. Prior to this point in time, you can find the area, in a square, in a triangle, in a circle, and shapes related to that, and shapes that you can break down, for example, into triangles. But that's kind of limited, and after a while you get frustrated with the number of triangles and whatnot that you have to put underneath the shape here. So what we're going to do here is we're going to take a look at the way you can use antiderivatives to find the area under some more complicated shapes here. So for example, what we might be looking at, we draw a graph like this. I don't know, it might be a function looks something like this, and then it continues on this way and whatnot. Now, when we say area under a curve, okay, so here's my y-axis, here's my x-axis. When I say area under a curve, what I'm referring to here is the area from the curve down to the x-axis. So area under a curve always refers to the area, okay, from the function to the x-axis. Now, if the function goes below the x-axis, then under the curve literally means above the curve, between the curve and the x-axis. It always means that. So before we get into showing you how the antiderivative works here, let me just kind of explain what it is that we're going to do here. Okay, so here's my function. Okay, here's my y equals f of x. So what I'm going to do is find the area from the function down to the x-axis, and I'm going to do this between some fixed left-hand point here, and then what I'm going to do is I'm going to let the right-hand side of my area here just be x. I'm going to be the variable x. Now remember, a is going to be a constant, x is going to be the variable part. So I'm just going to move this around here. So I've got a little bit of freedom to adjust this. And what I'm going to do is come up with another function that will give me the area under the curve. Okay, no matter where I put my x here. That's kind of my goal here. So now remember that this point right here is going to be the point a comma f evaluated at a, and this point right here will be the point x comma f of x. And then I am looking for this area under the curve, okay, and we're going to call this a of x. So the area under the curve as a function of that right-hand endpoint. Okay, so I'm fixing this left-hand endpoint, and I'm going to let this one be the variable in the function here. So whatever value of x I plug in there, what I'm hoping to get is a function that will give me all of that area there. Okay, so just write that out here. So a of x represents the area under f of x, okay, or between f of x and the x-axis. Remember that that's what that means here. Under f of x, beginning from a specified value, x equals a, that's our left-hand side, to an arbitrary endpoint. That is what this function is, this a of x represents. That's my goal. That's what I'm hoping to get at this point. Now, notice that the area that I'm coming up with is going to have this kind of box shape on one side. There's a good reason for that. And if we have more time and if there's demand for it, we'll go into why this works. Really what this lesson is going to do is really just show you how to use antiderivatives to achieve this goal. We're really not going to go into a lot of the detail of why it works. We can later on if that's of interest to people. We certainly can. But for right now, it's more important that you just understand what we can do with this antiderivative here. Now, one little note, okay, before we move on, just note here that based on what I've just done, if I take and evaluate my area function at a, okay, then what's going to happen here is I'm essentially describing a scenario where I take that x and I move it right here to this value of a. And so I'm really not getting an area, I'm just getting this little one-dimensional line segment there. So the area at a is going to be equal to 0. Okay, now notice, okay, at this point right here, this is my little like sub-note, if you will, doesn't this look like a boundary condition? So it looks like I'm giving you some information here that can be used to solve for that constant c. Okay, now, so this is my goal. So what I want to do is I want to kind of back off from a function that looks like this. Let's throw down a much simpler function here that we're going to find the area function underneath. And then basically we're going to generalize from this. Now this isn't really great mathematics in the sense of like I'm going to show you the ins and outs of how this works here. But I want to show you what is going on here, and then we'll just generalize to every other instance. So for example, what I want to do is I want to find the area, under, let's just make it a simple one. F of x is equal to x plus 2 from x equals 2 to some arbitrary endpoint. Okay, to some arbitrary endpoint. Now, let's take a look at what this looks like first so that we understand what's going on. So I'm going to draw my axes. Okay, now x equals 2, sorry, I'll just write this out here, make sure that that's clear. X equals 2, sorry, x plus 2, I think I said that twice there. X plus 2 is really just going to be a function that looks something like this. Y is equal to x plus 2. It's got a slope of 1, it's got a y-intercept of 2. Okay, and if I come over here and I start at an x value of 2, plug that in, okay, that's going to be out here at 4. This is going to be the point 2 comma 4. And what I'm interested in is coming up with the area underneath this thing out to some arbitrary endpoint x. So this area right here, this is going to be my area function a of x. Now, the nice thing about the example that we're working with right now is that this is a trapezoid. So without using calculus here, I already know what the area is supposed to be. Now, this may seem like I'm taking a bit of a step backwards here. Like I just told you that we're going to use antiderivatives to find the areas under the curve, and that we won't have to use these old formulas here. And now I'm going back and I'm going to pull out one of those old formulas here. But there is a reason for this, and I want to show you, okay? And the way to do that is to go back and use what we already know. So I know that the area of a trapezoid is going to be 1/2 the height multiplied by the sum of the two bases. Now in this case right here, okay, just because these are 90-degree angles here, the height is going to be the difference between those two. And then my two bases are going to look this way. Now basically it's just a trapezoid on its side here. So my function here is going to be 1/2. Well, the distance there, the height is going to be x minus 2. Now, the two bases here, okay, the two bases are the lengths of these two sides right there. Those are related to the function, x plus 2. And it's really important that you catch that, okay? That the value of the function is going to be the height on this side and the height on this side. Now, on the left-hand side, that's not a problem. That's just going to be 4. On the right-hand side, because we're stopping at an arbitrary value of x, it's hard to pinpoint exactly what that height is supposed to be. Okay? In fact, the best I can do is simply say that the coordinates of that point there are going to be x, comma x plus 2, the value of the function. So the best I can do right here with this base is simply write x plus 2. Okay? So now, this is going to be 1/2 x minus 2 multiplied by, well, x plus 6. And if I expand that out, I will get 1/2, and I'll just multiply this through. This is going to be x squared plus 4x minus 12. Okay? And so right here we've got a function for the area as under this curve, x plus 2, as a function of x. And I didn't even have to use calculus at all. Okay? Now, so I got to my goal here. I get my function right here. Here is the big, oh, wow, I can't believe that just happened. Let's take this function. Let's take my area function. Okay, my area function was 1/2. And I found it to be x squared plus 4x minus 12. Okay? And in fact, what I'm going to do here is I'm going to expand that. I'm going to multiply the 1/2 through. So I'm going to get 1/2 x squared plus 2x minus 6. Now, let's just take the derivative of this. Okay? Let's take the derivative with respect to that variable x there. So area primed, or dA by dx, is going to equal x plus 2. Oh my gosh. Look at that. Isn't that amazing? That the derivative of the area function is the original function that I'm trying to find the area under. That is amazing. Not only is that amazing, it's always true. Okay? It turns out that it is always true, whoops, that the derivative of the area function is equal to the function that we're finding the area under. Okay? So that little relationship, this is what we're now going to be able to take advantage of. Now, if you're not quite sure how this is all going to work, let's just take a look at an example or two. All right, so let's take a look at an example here. Find the area under y equals x squared plus 2, bounded by x equals 2 and x equals 4. Okay, now, first of all, what I recommend we do with a lot of these questions here is let's just take a look at what it is that we're looking at. So here's x, here's y. Now, x squared plus 2 is just a parabola, okay? It's got a y-intercept of 2. So here's my 2. Now, my drawing isn't going to be anywhere near to scale, but you'll get the right idea. Okay, so we're just going to have our parabola right here. We're going to look for the area between 2 and 4. So we're looking for this piece right here. This is, if you've never done this before, this is actually kind of exciting. It's kind of interesting here because we're about to find the exact area of a shape that isn't quite trapezoidal. It's got this little bit of a curve to it right here. Okay, so here's our area function. And actually, we are very specifically evaluating this area function at 4. So I'd like to figure out what this area function is first. And then I'm going to plug in 4 to get the actual area of this piece right here. Now, we just noticed that the derivative of the area function, so recall that the derivative of the area function is equal to the function that we're finding the area under. Now, what that means in this particular case right here is that the derivative of our area function is going to equal x squared plus 2. Now, this means that if we take the antiderivative of both sides here, okay, we are going to get the area function. Because the antiderivative of a primed is simply going to be a of x. The antiderivative of x squared plus 2 is going to be 1/3 x cubed plus 2x. Now all I'm doing is, remember, increasing the exponent by 1, dividing by the new exponent. But I got to remember to add c, that arbitrary constant. Okay, now that might look like a bit of a problem because now I've got this unknown here. How does this affect my particular question here? But remember, there is a bit of information that I can actually glean from this. guessing that there's this function that exists that finds the area from 2 to some value x here. But remember, okay, based on this diagram right here, if my area function is evaluated at 2, I know that the answer to that should be 0. So I can use that as a boundary condition to this particular function here. So I know, okay, but I know that a of 2 has got to equal 0, which means 0 should be equal to 1/3 2 cubed plus 2 times 2 plus c. Oops, I'm running near the end there. And if you put this all together, this is going to be, what is that, 8/3 plus 4. Put that together here. Move everything over, and I am actually going to end up with negative 20/3 as my value for c. Now I have the arbitrary constant. And so now I know a of x has got to equal 1/3 x cubed plus 2x minus 20/3. Now I have the function that will give me the area under this curve from 2 out to any particular value I want. Okay? So I want, in this particular case here, I want to know what the area is when x is equal to 4. Well, that's going to be 1/3 4 cubed plus 2 times 4 minus 20/3. Now, assuming that I did the math right before sitting down and doing this video here, that should be 68/3. And it's going to be units squared, whatever those happen to be, but 68/3. And there it is. That's the exact value of that almost trapezoidal shape that we've got right here under this curve. Just remember that it's got that little bit of a curve to it. It's not a straight line. And that's amazing how really little effort it took to get that particular value here. Now, before we go to do another example, I want to come back and I want to talk about this result just from a different direction. Okay, let's take a moment and let's go back and revisit this problem. We are trying to figure out the area under the curve x squared plus 2 between 2 and 4 here. And so what we did is we came up with an area function that had its left boundary here where a is equal to 2. And we got an answer of 68/3. But there is another way that we could approach this, and actually I really cannot overstate the importance of being able to see this problem in this way here. You're going to see this pattern of thinking show up over and over again from this point on. So let's just draw this out again. Let's just say that we've got our parabola here. Again, we're looking for the area under it from 2 out to 4. That's my goal. But now, everybody, instead of coming up with an area function that starts at 2 and goes to 4, what I'm going to do here is I'm going to come up with an area function that has an arbitrary endpoint, let's say over here somewhere. Let's just say at x equals a. Okay? So here's my value, my left-hand side here, and so I know that a of a is going to equal 0. So I know that a of 2, let's do it this way. Let's say a of 4 is going to be this area right here. Okay, this is going to be a of 4. It'll be the area from 4 back to little a here. On the other hand, a of 2 is going to be this area right here. Now, what I'm interested in is this area right here. So, going from a to 4 goes out to here, a to 2 goes out to here. What I want is the difference between them. I just want this leftover piece. So that's what I'm going to do here. Okay? Now, I don't know what my little a is, and so because that is an unknown to me, I don't really know what the arbitrary constant is. So from this assumption here, I actually don't know what a is. So my area function is going to go back to being what did I have there? I had 1/3 x cubed plus 2x plus c. Because I'm going to assume that I don't know enough to figure out what that arbitrary constant is. But it turns out that's okay. I don't actually need it. All I need to do here to figure out the area from 2 to 4, okay, that's not a point there, that's an interval from 2 to 4. And I suppose I could have made that a closed interval, but either way. All I'm going to do here is evaluate the area under my function out to 4, and I'm going to subtract that same function evaluated at 2. Now, this is going to end up being, when I plug this in, this is going to be 1/3 4 cubed plus 2 times 4 plus c minus 1/3 2 cubed plus 2 times 2 plus c. Turns out the c's cancel. Now, if you think back to some of the work we've looked at earlier, you might say, well, whoa, wait a minute. C's don't, when I combine c's, don't I just get another c here? And that is almost always true, except in this particular case here, because we're using the same function twice, whatever that value of that arbitrary constant is, it shows up exactly the same twice. So those two do cancel each other out here. And when you put everything together, you are going to get 68/3 units squared. So it turns out that my arbitrary constant here cancels if I know the two endpoints of the area that I'm trying to figure out. And so now I don't even need to find that arbitrary constant. Which actually leads to a statement here that we can make about how we generalize this. Let's take a look at it. Okay, so now we're going to kind of throw a statement out here in general about the way this works. So in general, if we're looking for the area under the curve y equals f of x between x equals a and x equals b, where a is less than b, so it just means to the left of b, then what we get is this. We're looking for the area function to be evaluated between a and b along this interval a to b. This is going to equal the area function evaluated at b minus the area function evaluated at a. And you know what we're going to do with this as well? And you're going to see why this is the case in just a little bit here, because remember what we said before about vectors being dominant in the work that we do, the calculus work that we do here. You're going to see a situation pop up in just a little bit where area will take on a negative value, which really doesn't make a lot of sense to us. There are contexts where it is important that that does happen, but because we're talking specifically about area here, we're going to drop absolute values there, just to make sure that that makes sense, okay? Or another way to think about it here, now, by the way, before I go on to my or here, where remember, a primed of x is equal to f of x, the original function there. Remember that that's what's going on here. Or another way to write this, kind of harking back to some of the work that we did just a little while ago here, is we would take the antiderivative of our function evaluated at b minus the antiderivative of our function evaluated at a. And again, we'll put absolute values around that. This little pattern right here, this f of b, the antiderivative evaluated at b minus the antiderivative evaluated at a, that is such an important pattern of work here, applying the antiderivatives here. You're going to see that come up over and over and over again. Okay, it's going to become just a part of the process when you're evaluating integrals, whether you're finding area or not here. Having said that though, let's take a look at another example where we apply this to find the area under a curve. Okay, so our last example that we're going to work through right here says find the area of the finite region bounded by y equals 9 minus x squared and the x-axis. Okay, well now before I do the math here to figure this out here, let's take a look at what this looks like. Okay, so let's just draw this out. There's my x-axis, my y-axis here. Now 9 minus x squared, that's a parabola that goes up to 9. Okay, it drops down here. Now, remember that when I'm finding the area under the curve, I always mean from the function to the x-axis. Now please, please don't be the person who goes, okay, well wait a minute, that's this bit right here, and then go, oh, but there's this section right here, okay, that opens up, that's from the function to the x-axis, this bit right here, from the function to the x-axis. Well, those pieces are going to be infinitely large. The answer is automatically infinity. No, don't do that. We even specifically wrote in this problem, I'm looking for the finite region. But even if I hadn't said that, the implication is always going to be that I'm looking for the finite region, okay, between the curve and the x-axis. So it would be implied that I mean between those two intersection points right there. Which, by the way, I've now got to go through and figure that out because I don't actually know what my A and my B are here. So I got to work that through here, and that's simply going to be those are going to be the x-intercepts of this graph. So that's just going to be 9 minus x squared is going to equal 0. So 9 is equal to x squared. So this is going to happen at plus or minus 3. That was pretty easy to find there. It's not always going to be easy, but in a lot of cases, that's not what we're trying to make the hard. We're not trying to make that the hard part of these problems here. So now the area underneath this, okay, is going to be the difference between the area function evaluated at two endpoints here, which will be -3 and +3. So what we're going to do here is, well, I'll do this in steps here. So I know that the derivative of my area function is going to be 9 minus x squared. Okay? So I know that if I take the antiderivative of that, I will get a of x. This is going to equal the antiderivative of my function. Okay, my little f becomes my capital F. We've seen that before. And when I look at this right here, that's going to be 9x minus 1/3 x cubed plus the arbitrary constant c. Now, I still need to keep writing that c there, even though in a moment here, that's going to not be an issue, but I still need to write it. I still need to remember that that is part of the process here. By the way, isn't it interesting that the area function underneath a quadratic is repeatedly cubic? Yeah. Maybe you think that's interesting, maybe you don't. I do. That's just an interesting little quirk of the way the math works there. Anyway. So we're looking for the area between -3 and 3. We already know that that is going to be the absolute value of our function evaluated at 3 minus our function evaluated at -3. Okay, and that is going to be, let's take a quick look here. That is going to be, well, the absolute value, that is going to be 9 times 3 minus 1/3 3 cubed plus c minus 9 times -3, oh, better make sure we can get that all in there, minus 1/3 -3 cubed plus c. Notice where the absolute values are going here. I see students struggle with this frequently. It's not around this portion and this portion. It's not around each individual little bit here. It's the whole expression here. It's the antiderivative evaluated at 3 minus the antiderivative at -3, and then I take the absolute values here. In this particular case here, I don't believe I need the absolute values anyway, but it's not a bad idea to have those there. This is going to become 54 minus 54 over 3, and the answer that I get, whoops, is 36. 36 units squared. And that is the area of that shape right there. Isn't it interesting that we're able to do that now? Now you can find the area underneath some fairly complicated shapes without doing breaking it up into a whole bunch of triangles and making approximations. Now you can get an exact value, and that's pretty amazing.